As I said, we're moving here in section 1.2 into a much more concrete place than where we were in 1.1. We're talking about estimates and rounding.
All right, so when the subroutine compounds the interest, right, it uses all these extra decimal places that just get rounded off. So we simplified the whole thing, and we round them all down and just drop the remainder into an account that we opened.
So you're stealing?
No, you don't understand. It's,
Where this should all, as I said, be pretty familiar material. Maybe review, maybe some slightly new things, slightly new terms, but hopefully it's stuff that you've at the very least seen before, if in a different way. When we're talking about estimations, we're talking about things being approximately equal to. And the reason why we care about things being approximate, especially using that symbol there, is because it can be clunky to deal with everything.
Which Power Ranger are you? Take this quirky quiz. Obama sent the immigrants to vaccinate your kids.
All at once. You can only handle so much of everything all of the time. Where, for example, a thing like pi, the value describing the ratio of a circle's circumference to its diameter, what we're talking about there is an infinitely long number. It goes on forever and ever and ever. So you might think to yourself, if I want to write that number out, I have to keep writing forever and ever and ever. But the truth is, you don't actually need all of those values. For most everyday usage, people are happy with just 3.14, maybe 3.14159 or something like that. Or even NASA, the foremost authority on computations as far as I'm concerned, they only go up to 15 digits. Because you don't really need more than that, even for something as complex as measuring, or estimating anyway, the diameter of the known universe. Point is, we don't need every single number. We don't need everything. Usually we can get close enough. When we're talking about getting close enough, that's when we're talking about things with rounding. When we're talking about rounding, we do need to get a little bit more exacting with our idea of the natural numbers, which I mentioned last time. Those are our counting numbers, as it were, 1, 2, 3, and so on, where according to some definitions, 0 is included. For us, we're going to say that including 0 or adding 0 gets the whole numbers instead. Then if you get the negatives, you're getting things called integers, but something else. We'll talk more about exacting definitions of these things later. Point is, we're talking about these values there, and why they're called the natural numbers should be pretty obvious. It's because they're the most natural numbers there are. Numbers kind of exist for counting. These are great for counting. These are easy to work with. Hence the name. So if we want to deal with these things, that's great, but a lot of numbers are like pi. They don't naturally fall into the natural number pattern. And that's where rounding comes in. That's where we get this idea there of getting closer to a natural number or a 10 or a decimal or something else. We just want to get closer to a value that's easier to deal with. We want to get closer to something that's close enough for our purposes. Where the general scheme we follow is to round to the nearest number. And we do that in terms of basically fives. Where if we're rounding to the next thing up, then we are looking for values that are 5 or above. And then when we're rounding down, we're looking for things that are 4 or below. To be a bit more exacting in our process here, which hopefully you know, when we want to round, what we do is look at the digit to the right of where rounding is to occur, then see if it is 5 or greater, in which case we add 1 to the digit to be rounded and kill off everything else. If it's less than 5, then you don't change it, and again, lots and lots of death. So, really simple example. If we wanted to take a value like 3.7 and round to the nearest whole number, the nearest natural number in this case, what we would recognize is that the value here of 7 is bigger than 5. So, rounding to the nearest whole number would give us that 3.7 is approximately 4. And depending on what our purpose is, that might be good enough. So let's get a quick example here in terms of understanding both why we would want to do this, as well as, I guess, how we could do this. So for this example, we want to round 478,329 to the nearest thousand and 6.72961 to the nearest thousandth, where, for these examples, in that first case, the 478,329 will be rounded down. to 478,000. Flat. Because this next digit, the 3, is going to be less than 5. So that doesn't change, those all get rounded down. And again, reason for this is because with a number that large, for our purposes, the 478,000 is probably enough. Obviously, depending on what that 329 is, it might be a bit impolite. Those might be people you're discounting. It might be money you're discounting. People like their money a lot. But for the purposes of quick math, for the purposes of being able to do this stuff maybe by hand, or just get a fast guess, because I don't want to just say estimate again, that's probably enough. Meanwhile, for our second case, when we have that 6.7, I'm losing my number there, 2961, we should remind ourselves that the 7 is tenths, 2 is hundredths, thousandths, 10 thousandths, and 100 thousandths. The 9 is in the thousandths, so we're going to 1 beyond that, to the 6, where we will recognize that the 6 there is bigger than 5. So what we will end up with is 6.7, 9 becomes 0, carry the 1, 3, 0. And again, in this case, those values might be very important in certain contexts, but most of the time, these 3 digits will get the job done, or at the very least be close enough that we can understand where we should be looking. So let's get one more example here to understand why we might actually want to do this, because usually we've got a calculator in hand and we get all these things a bit more exactly, but maybe we do need to do something a bit quickly. Let's see what happens in such a case.